The ocean absorbs about 25% of all the carbon dioxide humans produce. That sounds like a good thing, right? The ocean is cleaning up our mess. But there's a catch. When CO2 dissolves in seawater, it forms carbonic acid. And over the past 40 years, ocean acidity has increased by 17.5%. The ocean floor is literally dissolving, and it barely makes the news.
17.5% more acidic in 40 years? That seems like a lot.
It's enormous, and to understand why, you need to understand how the pH scale works. pH is logarithmic, meaning each full unit represents a tenfold change. Since the Industrial Revolution, ocean surface pH has dropped from about 8.2 to roughly 8.1. That might look like a tiny number, but that zero point 0.1 unit drop represents a 26% increase in hydrogen ion concentration. The Copernicus Marine Service measured the 17.5% increase just between 1985 and 2024.
And we're still pumping out CO2, so it's accelerating?
The rate is roughly 0.002 pH units per year, and projections from the European Environment Agency show that by 2100, ocean pH could drop by an additional 0.5 to 0.5 units depending on emission scenarios. The worst case scenario would represent a 150% increase in acidity compared to pre-industrial levels. Nothing in the geological record suggests ocean chemistry has changed this fast in at least 300 million years.
300 million years. What happened then?
The Permian-Triassic extinction event about 252 million years ago, the Great Dying that wiped out 96% of marine species. There's evidence that ocean acidification from volcanic CO2 emissions was one of the contributing factors. We're not at that level, but the rate of change today is potentially faster than what the Permian oceans experienced.
That's genuinely alarming. But what does more acidic ocean water actually do to marine life?
The most direct impact hits organisms that build shells or skeletons out of calcium carbonate. That includes corals, oysters, mussels, clams, sea urchins, and a group of tiny organisms called pteropods, which are essentially sea snails that swim. When ocean water becomes more acidic, it binds up carbonate ions. The building blocks these organisms need. Less available carbonate means it takes more energy to build shells. In severe cases, existing shells start dissolving.
Their shells dissolve while they're still alive?
In laboratory experiments, yes. Researchers at the Smithsonian's National Museum of Natural History have documented pteropod shells developing visible pitting and erosion when exposed to projected future pH levels. In the Southern Ocean, where cold water absorbs more CO2, researchers have already found wild pteropods with corroded shells.
And pteropods might sound insignificant, but they're not, are they?
They're a critical link in the marine food chain. Pteropods are a primary food source for salmon, herring, mackerel, and many whale species. In some Arctic and Antarctic ecosystems, they're the base of the food web. If pteropod populations collapse, the effects cascade upward through every species that depends on them.
What about coral reefs? They're already under stress from warming. How does acidification add to that?
Coral reefs face a brutal double threat. Warming water causes coral bleaching, where corals expel the symbiotic algae they depend on for food and color. Acidification attacks the skeleton itself. Corals build their structures from aragonite, a form of calcium carbonate that's particularly sensitive to pH changes. As the water becomes more acidic, corals have to spend more metabolic energy maintaining their skeletons, leaving less energy for growth, reproduction, and recovery from bleaching events. A study in PMC found that ocean acidification degrades coastal habitats including coral reefs, seagrass beds, and kelp forests with cascading effects on the ecosystem services these habitats provide: coastal protection, fisheries, tourism, and carbon storage.
Wait. The ocean absorbs CO2, but the CO2 is destroying the ocean's ability to absorb CO2.
That's one of the most concerning feedback loops. Healthy oceans with thriving ecosystems act as carbon sinks. Coral reefs, kelp forests, and phytoplankton all capture and store carbon. As acidification degrades these systems, the ocean's capacity to absorb CO2 could diminish, leaving more CO2 in the atmosphere, which accelerates warming, which makes the ocean absorb even more CO2 in the short term, which accelerates acidification. It's a vicious cycle.
Why isn't this getting the same attention as atmospheric climate change? You hear about rising temperatures constantly, but almost never about ocean pH.
Scientists have been calling it the other CO2 problem for over a decade. Part of the issue is visibility. You can feel a heat wave, you can see a wildfire, or a melting glacier. Ocean acidification is invisible to the naked eye and happens below the surface. It's also slower moving than extreme weather events, which makes it harder to turn into breaking news.
But the consequences are just as severe.
Potentially more severe in some ways. Roughly 1 billion people depend on marine protein as their primary source of animal protein. Fisheries and aquaculture generate over $150 billion annually. Shellfish industries in the Pacific Northwest of the United States have already reported oyster larvae die-offs linked to acidified water.
Oyster larvae are already dying.
The Pacific Northwest shellfish industry experienced significant production losses starting in the mid-2000s when upwelling brought deep CO2-rich water into the shallow areas where oyster larvae develop. Hatcheries had to install monitoring systems and adjust water chemistry just to keep production going. It was one of the first economic wake-up calls for ocean acidification in a developed nation.
Is there anything we can do to reverse this or at least slow it down?
The honest answer is that the only real solution is reducing CO2 emissions. The ocean's chemistry will eventually rebalance, but natural geological weathering processes that neutralize acidity operate on timescales of thousands to tens of thousands of years. There are no shortcuts. Some researchers are exploring localized interventions like adding crushed alkaline minerals to coastal waters to buffer pH, but these are stopgap measures at best.
Thousands of years to recover, and we changed it in decades.
That asymmetry is the core of the problem. We can acidify the ocean in 200 years. The ocean needs 10,000 years to fix itself. The only variable we control is how much worse we make it before the curve starts bending the other direction.
A 17.5% increase in acidity in 40 years. Shells dissolving on living animals. The base of the food chain under threat. A billion people who depend on marine protein, and the ocean itself losing its ability to protect us. That's the story hiding below the surface.
The other CO2 problem, and it deserves to stop being the other one, sources linked below.